All right, this is my presentation on reaction rates. All right, so what is reaction rate? So reaction rate is a measure of how quickly a reaction proceeds, or how quickly reactants are turned into products. And it's defined as the change in concentration of the product of reaction over time. And when you're comparing reaction rates between two different reactions, the dissolving of like table salt in water has a much higher rate of reaction than the forming of rust on iron does, because the product dissociated salt ions, or Na and Cl ions, appear much more quickly than the products in rusting do. So much higher rate of reaction there. And what factors affect the rate of reaction? The nature of the reactants affects this. Molecules with weaker bonds will react more quickly, and thus have a higher reaction rate because those bonds will break more easily to form products. And then more concentrated reactants will also react more quickly because there will just be more collisions, which will increase the rate of reaction and form products more quickly. Surface area also will affect the reaction rate. If you increase the surface area, you'll increase the number of correctly oriented collisions, which will increase the rate of reaction. And then lastly, the temperature of the reactants also affects it, because higher temperature will increase the average kinetic energy, and this will lead to a greater number of collisions, and thus a higher rate of reaction. And then lastly, the addition of a catalyst will also increase the rate of reaction by decreasing the activation energy, which we'll talk about in a minute. All right, so this is reaction order and the graphical determination of reaction order. So zero order, which is up there on the left, when you graph the concentration of the reactant being monitored against time, it is linear. And then with first order reactions, which is just on the right of that, when you graph the natural log of the concentration of the reactant being monitored, it is linear. And with regard to first order reactions, half-lives, or the amount of time it takes for half of a given substance to go away or decay, can be used to determine the rate constant by the equation T1 half, or the half-life, equals 0.693 over K. And then second order reactions, the inverse of the concentration, or 1 over the concentration of the reactant being monitored, tracks linearly with time. So if you look at the graph of a reaction, you can determine what order it is. And then energy profiles and activation energy. So an energy profile, like the one you see on the right, is a graphic representation of the potential energy of a reaction over time. So as you can see for this one, which is an exothermic reaction, potential energy increases and then decreases from the reactants to the products. And that gap between the line with the reactants and the top, the activated complex, that's a graphic representation of the activation energy, which is the energy required to get the reaction to basically commit to making product, or at that point, like all the bonds have been broken and it's creating product at that point. And Maxwell-Boltzmann distributions, these are graphic representations of the number of collisions with a certain amount of energy in a reaction. And these will be affected by temperature and catalysts and other things that affect it. So this graph here shows how an increase in temperature will make more collisions in the reaction, have sufficient energy to overcome the activation energy barrier. As you can see, the distribution of the highest temperature reaction, which is the green one there, has it crosses the activation energy at the highest point, so it has the most collisions that reach the activation energy. And then this means that the reaction will proceed at a higher rate. So that's, kind of another way of showing why temperature increases the rate of reaction. Thank you.